This is the USGS National Geospatial Program Hydrography Advisory Call. And today we've got lots to talk about. So I'm going to try and go ahead and get started here. And the first announcement, which we just got in here, this was in the newsletter that we sent out last week, I believe. But, you know, we are moving some of our operations between our locations at the NG Talk between Denver and Rolla, Missouri. And so we're going to be shut down from the 23rd, which was last Friday, till May 9th. So right now, you can't do checkouts for either NHD or WBD and can't do check-ins. During this time, we're asking that you please update your tools. If you're a steward and you're working with the tools, our update tools, we're asking that you update to ArcGIS 10.7.1 and update the tools with the version that you can get on the HDC, the Hydro Data Community. That's the main announcement I wanted to make. Was there anything else that I needed to cover on that, Becky?
Nope, I think that's it.
All right. Okay, and Vanessa's put some information in the chat about where you can pick up the recording of this on our YouTube channel. It'll be showing up there in the next few days. So we'll go ahead and get started with what our main topic today is, which is basically we're going to talk about sort of three things, and they're all pretty closely related. We're going to talk about a national data release of the NHDPlus high-res, which is going to happen real soon. We're going to talk about generalizing the NHDPlus high-res, and we're also going to talk about the problem that we have with the NHDPlus high-res, which is directly inherited from the NHD itself, and that is a lot of disconnected network. So those are our three main topics, and I'm going to start here with the NHDPlus high-res, and just to kind of reiterate, this is the map hasn't changed a whole lot, although we've added a couple of units, I think, in Alaska recently. But we've had the CONUS, the Conterminous US, we've had finished in the beta version of NHDPlus high-res for a few months now, since late fall last year. We are going to be coming out with a national data release, which we're going to call National Release 1 of the NHDPlus HR in the next few weeks, probably. We've got a candidate data set that we've had a few people review, and everything is looking pretty good. We have a few issues to fix on it, but we're getting really close to being able to release that. It's going to be a national data set. It will have some updated value-added attributes, updated VAAs, because as we produced the data, especially if you think of it in terms of the Mississippi River Basin, you know, we did like region 10 and 7 way back, like 4 or 5 years ago almost. And then, you know, we finished region 8 just last fall. And so there are four attributes in the value-added attributes that get updated as we process the data from upstream to downstream. And then at the very end, those get updated all the way back upstream. So it's things like what's the terminal path identifier of the last flow line in the network, which I'm going to show in a minute. All of that, and like the distance from what we call the path length, the distance from the point of interest downstream to the end of the network. So things like that get updated as we go through, but we're not going back and reposting all of these. I don't know how many there are, 100, close to 100 maybe, VPU level 4-digit HUC data sets for all of the Mississippi Basin, for example. We're not going back to update all of that later. But it is going to be, all those updated VAAs are in this national release that we'll be releasing real soon. So want to just give you a little preview of that. And of course, as always, you know, we invite people to review and provide us feedback through the markup application if you find issues in any of this beta data sets in the NHDPlus or in the NHD or WBD for that matter. So again, just a reminder about the NHDPlus, or I'm sorry, the markup application. You know, anyone can go in and provide a suggested edit to us, and we will get it in the queue to get fixed. So I'm going to do just a very brief overview of some of the value-added attributes that are changing in this new national data set, just to kind of give you kind of a preview of what to expect in that. So just a reminder about the value-added attribute stream level. Stream level here, we basically start at the coastline of a river network. We work our way upstream. A stream that flows into the coast is a level 1 stream. We work our way upstream, and each time we come to a confluence, we decide which of the 2 paths coming together there is the major path, and we follow that major path upstream, and we call that all the level 1 path, right? Then anything that's a tributary to a level 1 path is a level 2. And then anything that's tributary to a level 2 path is a level 3. So we're showing some of those here. So the level path, that's what a level path is. And then we have level path. We have two attributes. The level path identifier is the hydrosequence number of the last flow line in the network. So what I'm showing here is the last flow line in the Mississippi River down at the Crow's Foot, or where it goes into the Chicken's Foot. I forget what that's called. Down at the Delta, in where it flows into the Gulf of Mexico. The last line in that network, and you know, we get the hydrosequence number from that, and you can see if you select the level path ID, you're going to get the Mississippi River Basin all the way to its headwater. If, on the other hand, you select the terminal path identifier, having that same number, the hydrosequence number of this very last flow line, you're going to get every flow line that flows into the Mississippi River. So here's what that looks like. This is the level path identifier. We did a query on that. And this is that national data set that I was just referring to, that national data release. This is the preview version of it. And this selection took like a minute or a minute and a half maybe. Took quite a lot longer than that to draw all the lines, but it's pretty handy to have it all in one big data set. This is showing the terminal path ID again. So it's every flow line. We're highlighting every flow line here that flows into the Mississippi River and out through the Bird's Foot. Someone added that in the chat. Thank you. Down into the Mississippi Delta. So that's just a preview, really, of the kind of analysis that could be done with this national data set. The national data set is really big. It's about 25 gigabytes, if I recall. So it's, you know, it's a big download, but it's really useful because you can do this sort of analysis spanning the entire data set. Just a quick reminder of what some of the other value-added attributes are. Here's a list and a link to the webpage on value-added attributes. Lots more information there on that webpage about the VAAs. So just wanted to give you sort of a taste of that national data set. Next, what I've got is I've got a quick slide. This is from Shelley Cawley at EPA. Shelley's not able to join us today, but she did provide a slide with narration. So if this is going to, hopefully this is going to work right, and you'll be able to hear Shelley's voice describing some of what some of the rationale and why this generalization effort for the NHDPlus high-res is being undertaken. And so here is Shelley.
Hi, my name is Shelley Cawley, and I work for the EPA Office of Water in a water data integration branch. I'm going to set the stage for this discussion today by giving you a little bit of background on EPA considerations. The EPA has a very active community of users using the NHDPlus, the original NHDPlus medium res or 1 to 100,000 scale product. In fact, it seems as if this community of users is still growing. At the national level, at the EPA Office of Water, we do a lot of activities such as tracking and assessing and monitoring and modeling that are very well suited to this resolution data set. For our national activities, having a data set that is nationally consistent and having a network that's traversable for upstream and downstream searches is necessary. We also have quite a few users within the EPA community that have begun moving towards the high resolution product. At the EPA regional level and with our state and local stakeholders, there are many activities such as permitting. More recently, Clean Water Act jurisdictional determinations have been much talked about, cleanup efforts and Superfund and criminal enforcement activities. These are all things that are well served by a high resolution product. So as we pause and take stock on how to best serve this diverse community of users, the final consideration that really helped us with our path forward has to do with the push, especially within the EPA, to adopt the principles of the Internet of Water. And one of the main pillars of the Internet of Water is to use a common hydrography. And to adopt a common hydrography would really be a motivation for us to try to usher all of our users into a shared data set. All of these considerations taken together really drove us to the concept of generalization and the methodology you're about to see.
Next up, we're going to have Cindy McKay talk about this generalization concept with the NHDPlus high-res.
I'm going to give a few abbreviated notes right here at the beginning to complement what Shelley said. EPA, most states report to EPA using high-res NHD. And so for the past, many years, EPA has spent a great deal of time moving all of the things that they have linked to NHDPlus version 2, which is medium res. Link all the things that states send to NHDPlus medium res so that they can do their national applications and tracking. During the past several years, there's been a strongly advocated need for updating NHDPlus version 2. Lots of people have updated it on their own. These have not been particularly useful to the larger NHDPlus community. They've been for specific applications. But now that we have high-res NHDPlus, EPA has decided now is the time that we need to move there so that everybody is on the same playing field in terms of linking information and sharing information. The high-res NHD has some very strong aspects to it. First of all, it has stewardship. I'm sure many of you on this call are the stewards. And the stewardship comes from states and federal agencies. And also at any specific location, it is generally the most detailed scale of hydrography available. And finally, the data tends to stay current with on-the-ground conditions through photo revision and updates from LiDAR and IFSAR sources. But it has two major disadvantages, which sort of stem from its advantages. The number of features in high-res NHD is 10 times the number of features in medium-res and NHDPlus. And high-res NHD and NHDPlus have extremely varied densities across the lower 48 states. Many places are 1 to 24,000, and a lot of places are becoming 1 to 2,000 or maybe even denser. So the idea of generalizing the NHDPlus high-res started to take shape, and that's what we're here to talk about. I wasn't hearing what was going on, but I saw some slides that Al was showing about the NHDPlus. This is just a snapshot of what's in NHDPlus, and it doesn't matter whether it's medium res or high res. This is it. You have the snapshots of the NHD, the 3-depth elevation, the watershed boundary data set. You have all the wonderful attributes that have been added: flow volume and velocity, the USGS gauges and streamflow measurements, all sorts of evaluated attributes, and you have the catchments, which is really what NHDPlus is all about, because that links the stream network to the landscape. The objective of NHDPlus high-res generalization. The first objective was to enable users of NHDPlus version 2 medium res to become users of NHDPlus high res. NHD high res, as I said, has nearly 10 times the feature count. So the stated requirement for generalization was create a less dense stream network to support models and processes that have software that has feature limitations and or high performance requirements. Here's a picture of the feature volume difference. On the left is NHDPlus version 2. On the right is NHDPlus high res for the same area. You can see the counts down in the bottom. We have 2.7 million features in the medium res network, and we have 26 million. And actually, this slide is probably out of date. It's probably more than that now in the high res NHDPlus. It's interesting to look at the lakes. There are about 10 times more lakes 17 times more lakes in high-res NHDPlus. But if you look at the lake area, it's 241,000 versus 442,000, which is only about double. What's happened in high res is many, many, many very tiny lakes are now in the NHDPlus and NHD. The second objective for the generalization was to take the best available data that's in high res and address the extreme differences in stream density. And use the generalization process to do an NHD high-res derivative that was more consistent across the country and hydrographically based rather than cartographically based, which is what it is now. Here's an example. This very, very dense area in the southern side of this Huck 4, that's from LiDAR. The rest of it was probably mostly from 1 to 24,000, but you can see there are a lot of areas that have been densified, and there's an extreme difference across this Huck 4. The third objective is to encourage users to adopt a single hydrography data set, as Shelley said. That will be the standard reference layer for linking all external information to the surface water network and to water bodies. And that was the stated objective of the generalization, to establish a derivative from the standard reference layer that still links back to the standard reference layer. So if you adopt a generalized high res, you haven't left high res. You still have the identifiers that you can go back and forth between high res and the generalized version. The main way of linking data to the NHD and to the NHDPlus is through the reach code. And this is a picture of where we stand on reach codes. When high-res was built, NHD high-res was built the first time, the medium-res reach codes were conflated onto the high-res line work, and there was pretty close to 100% agreement between medium-res reach codes and their representation in high-res. On the left-hand side, you see medium res. The red lines are the ones that have reach codes that are still in high res. The blue lines have reach codes that are no longer in high res. And that same color scheme is used on the right for high resolution. You can see that there are still a lot of flow lines that have the same reach codes, but there's a whole lot of blue lines that don't. There is about, when we did it, counted this probably a year ago, there was a 70 to 75% correspondence between medium and high res using reach codes. So our generalization technique is pretty simple. It's 3 steps. The first is select the desired stream network that you want. And we left this as sort of a user activity. And then we developed the rest of the generalization technique to take a user's selected stream network and turn it into a generalized high-res NHDPlus. You can select the network using the high-res visibility filter. This is an attribute that's in NHD high-res. It's very good, but it does have some limitations. You can use high-res NHDPlus attributes like stream flow. You can use points of interest. You can take permitted discharges and just keep the network that's downstream of permitted discharges. Or you can just pick a random area of interest network out of the middle of NHD, and that can be your desired stream network. Then we have a tool that will prune the stream network of all unwanted surface water segments. In other words, everything you didn't pick, it will remove. And then there's a generalization tool that takes NHDPlus high-res components and generalizes those to match the prune network. I have to say that in the generalized version that we are currently creating, we wanted to preserve the NHDPlus evaluated network attributes as much as we could. So we added a small number of pruned flow lines, ones that have been discarded, back into the network, the selected network, for level paths and for named paths. We wanted the whole Mississippi. We wanted the whole level path for a stream. Then we generalize the catchments. We navigate downstream from a pruned or removed flow line until we get to the network that has been selected. And we dissolve all the catchments that have been navigated into that selected flow line's catchment. We adjust some of the NHDPlus attributes. Most of them survive the generalization without adjustment, but a few do not, and we adjust those. One set of attributes we have not adjusted yet, which we could, is stream order. Stream order doesn't seem to make a lot of sense in the generalized network, but we're sort of waiting to hear from end users to find out if that's a true statement or not. And if they want stream order, there is software to generate it, and we can do that. The other thing that's in the generalized network is a crosswalk. Every single flow line that is removed is crosswalked to the flow line that receives its flow. So everything, as you navigate downstream and you gather up all the catchments and dissolve them into the flow line in the network, you also crosswalk all those flow lines that you've navigated to that flow line that's in the selected network. We use the left-hand side of this to do our generalization. For the most part, we use the visibility filter. But there's nothing to say you can't just pluck a partial watershed out of the network and use the NHDPlus generalized catchments as the upstream boundary conditions. There was another discussion about whether we wanted to combine features and thin the coordinates. We have opted not to do that, mainly because if you combine features, you start losing the reach codes and you start losing F codes. Of course, you could always limit the combination on F code, but we just decided it was better to keep all the features than do that. Thinning the coordinates was another thought. That will change the measures along the reaches, so it will change how things are linked. So we have also left that as a maybe someday to do if somebody really needs that and doesn't care about reaches. Here is a HUC4. We picked a network, dark blue lines here, just out of the middle of this HUC4. And then we generalize the rest of the HUC4, and we end up with this. So now you have this little generalized network, and you have these big catchments here that drain into the upper end of this network, and they can provide all the boundary conditions from upstream. Here is a picture of the visibility filter. I'm sure you've seen this probably many times on this call. It has 9 values. There are 8 listed here. It also has a value of 0 where visibility filter hasn't been assigned. And that's generally lines that have been added from LiDAR or IFSAR and are less than 1 to 24,000 scale. Basically, the visibility filter is trying to tell you what lines are added to the map at that map scale. So here's 1 to 5 million, 1 to 2 million, 1 to a million, 500,000, 250,000, 100,000, 50,000, and 24,000. So that's what the visibility filter does for you. And it's a very handy way to do a first level of pruning on the network. But we decided it was not necessarily the be-all and the end-all of the prune network. So the goals of the ongoing project are to design and develop first version of the tools to generalize NHDPlus high-res. And then we want to build a user tool that will create a generalized NHDPlus data set from a user's pruned NHDPlus high-res flow lines. We have the tool. It is not ready for prime time in the sense that it has very little documentation, and it hasn't really been turned into something that you would want to give to a user and hope that they could understand it and use it. We want to test the tools on users' pruned NHD data sets. So if people want to send us data sets, we'll try the pruning tool and send them back to pruned NHDPlus and let them see how it worked out. And most importantly, we want to create a national generalized NHDPlus high-res that has the network density and usability of the medium resolution NHDPlus version 2, but it still links back to the high-res NHDPlus. Here is the visibility filter applied to 0602, which is the middle of the Tennessee. And you can see that it really, smooths out this huge dense area over here and other dense areas. We ended up using 1 to 250K. We tried a lot of Huck 4s across the country, and 1 to 250K was a little too dense, but 1 to 100K was way too dense. So we stuck with 1 to 250K, and we have actually run the generalization process on the lower 48. And if you look at the stream miles that are in the generalized data set, it is really, really close to NHDPlus version 2. Zooming in, here's a closer look at what we did. These are the flow lines. When we pruned, the green ones went away, the blue ones remained. Here is the crosswalk to show you that, this helps you figure out where a pruned flow line ended up in the network relative to its catchment area and its attributes. Here's an example closer than specifically of the crosswalk. These little yellow lines are in this table, and you can see that all of them discharge to 26,115, which is this guy down here. I hope you can see my cursor. The crosswalk table also tells you how much network had to be traversed in order to get from the flow line that was pruned to the flow line that was selected. Here's the catchments. You can see each flow line has a catchment, even the green flow lines. But because they were removed, we want to get rid of their catchments. And here's what it looks like once those catchments have been removed. Let you look at that just for a second. Okay. It's a little easier to see when you take away the green lines. You can see that each flow line still has a catchment, but the catchments have gotten bigger, and they represent all the tributaries that were pruned out. So the benefits of generalization. These alternative versions of NHD and NHDPlus can trade information by all having a crosswalk to the high-resolution NHD and NHDPlus, and thereby to each other. We hope we've enabled national, regional, and local modeling with less dense networks, and results of these modeling efforts can be combined. We've created versions of NHD at desired drainage densities that still have the spatial precision and attribute richness of high-res NHDPlus. And we provided a migration path for NHDPlus version 2 users. Shelley mentioned that community is still growing. In fact, the other day we got an email going, "What happened to version 1?" EPA had taken that off their website, and people still wanted to get it. So we've provided this migration path for NHDPlus V2 users by supplying a similar surface water network based on high-res. And we've allowed, we hope, NHDPlus to move forward as NHD high-res, 3-dep elevation, and WBD are updated. Sticking with NHDPlus V2, that was a very heavy lift to do that. But now that all we have to do is run an automated generalization process, I think generalization can keep up with the high-res maintenance. There are, if you haven't heard, a lot of isolated networks in NHD high-res. And we would like to resolve those in NHD generalized and also NHD high-res. And Rich has developed some techniques and procedures, and he's going to talk to you about those. And so that's our next step in this work.
Pete McCarthy is asking, will events and data that have been attached to NHDPlus V2 be conflated to the generalized NHDPlus HR?
We certainly hope so. EPA is going to have to do that. Well, I'm saying that the EPA events that are on NHDPlus V2 that EPA uses for their national analysis and tracking will get moved to the generalized data set. There are a lot of things out there that have been put on medium res by others, and we're hoping that folks will take the initiative to move it to generalized. Keep in mind, we still have a reach code correspondence that will probably do a lot of those events. We have not figured out the percent of correlation of reach codes between medium res V2 and high res NHD, but we will do that. That's been on my list here for a few weeks, and we'll figure out whether it's still just 70 and 75% or whether it's gone up, because what we've eliminated is a lot of the new dense stuff.
Great. Okay, so we'll move on a little bit now. And I want to just talk about disconnected networks, because Cindy she briefly mentioned the idea of isolated networks and disconnected networks. And I want to just, that's going to be the topic that we're going to spend the rest of the hour talking about here. And, just want to point out that there's quite a bit of this, and I think most of you have seen cases like this where we have lines that just don't connect to the network, to the main network. And this was, this is common in the NHD, and it's really kind of going back to the source, which was the USGS topo maps. Generally, these were a cartographic product, and generally, if the analyst the cartographer couldn't see a channel in aerial photography, they didn't draw it. That was sort of the rule. But from a hydrologic standpoint, particularly from a hydrologic modeling standpoint, we need that network to be connected. We don't want it to be completely isolated, as if any water that falls on the catchment for these lines just will never make it to the stream network. So we need some way to handle that. So how big a problem do we have? It's a pretty big problem. So using the NHDPlus HR value-added attributes and that national data set, the national data release that I showed earlier, this is what we have in the data set, 250,000 of these network ends. These are places where the network stops that are not at a coastline. Now, a lot of those, a lot of those, nearly half of them actually, are single isolated flow lines like the ones that I just showed. So we can remove those pretty easily just by querying them out. And in fact, in NHDPlus medium res, those single isolated flow lines were treated that way. They were just ignored in NHDPlus medium res, and that's what we plan to do with NHDPlus high res when we update. we're going to just ignore those single isolated flow lines because there's so many of them, and they don't really contribute that much to the whole picture. So we're going to just ignore those. So, but that still leaves us with 140 some thousand, isolated networks, and we need some way to deal with those. This is a histogram looking at how much contributed, total drainage area those networks accounted for. That that 140,000 plus flow lines. The vast majority are pretty small in terms of their drainage area. The cumulative drainage area being, at the end of that network that's isolated. So, the vast majority are under 2 kilometers, under 2 square kilometers. And then there's this long tail of lots and lots of, larger ones. And if we go out to here and look at everything that's larger than 50 square kilometers, we do have a sizable number of those. So what we've been doing is we've been looking at larger drainage area networks that are disconnected, and we've been trying to figure out how to connect those up. But Rich is going to talk next about a process that we're going to try to use to try to identify how we can connect up these really large numbers of isolated networks. So Rich, I'm going to stop sharing and let you share your screen and take it. It's good, Rich, and we can hear you fine. So.
Great. Yeah, what it is, it's this tool that's been created. It's called Fill and Spill, and it starts with the downstream end of each isolated network, and tries to create a path from that point down to where it will hit a flow line, another flow line, basically. So the purpose is to connect up these isolated networks to downstream high-res flow lines. And it was the tool as it exists now was created by Justin Myers, and it was basically done following the work of Curtis Price, who created the prototype for it. And it's written in Python, and it uses ArcPro, tools to do that, processing tools. It's mainly a raster process that it does, because it's working off of either the hydrodem or the elevation model, the DEM. And what I've done here is shown in black the locations of the existing flow lines in the NHD. And actually, it's a product that comes with the NHD called the Surface Water Network. And it's a raster data set. And what we're doing is following the sink at the downstream end of these networks, and following it down to the next flow line. And in this case, it's one of those isolated networks that Al just spoke of, and that will be not used in the next version of the high-res NHD. It is in the existing version, the beta version. But anyways, it goes down, identifies the path down to this flow line, and then from the end of that isolated network, you can see the secondary path, the second path going down to the next network. And so this geometry is available, and these green lines are created from the existing elevation DEM. We call it's L of CM is the file name. Here are other examples. You can see 2 flow lines coming together and ending. It creates a connection all the way down to this next network. Again, 2 flow lines coming together, and the missing link is put in there. As Al said, there are a huge number of flow lines that are disconnected. This is for CONUS. It's a huge number. And what I've done here is shown how many disconnected networks there are by hydro region in the first column, and in the second column, looking at by HUC4s, looking at the worst. This is the extreme cases in hydro region 16, and it's the 4-digit HUC 1606. We picked that one as sort of the worst case scenario to test. And I've also looked at looking further down the list. I picked 1401 in Colorado to be the sort of one more typical of what you might find. Average count is 1,081 sinks or isolated networks in that one particular HUC4. There's pretty close to the same number, 1,040. So these are the two areas that were selected for testing. The one in Nevada is huge, and actually it looks a little bigger than it is because it's got the width of the circles, of the selected circles, the sinks at the end of these isolated networks. But the one in Nevada and the one in Colorado are done for testing. And I'm just going to talk about the Colorado one because of the time constraint, and Nevada has a lot more complexity to it that we are able to address as well. But in this particular HUC that was picked, there are 5 different 8-digit HUCs, and the program works more efficiently by doing it by 8-digit HUCs. So it cycles through these different HUCs, and you can see this has a count by 8-digit HUC. This shows you the geographic distribution of the sinks at the ends of these isolated networks, all 1,040. This particular HUC is, if you're familiar with Denver and going up over Loveland Pass, it's just over. As soon as you pass the pass, you're in that HUC. And so these are all what we're trying to connect up. And running the program, Justin Meyer's program, I've highlighted in this illustration the fill and spill lines. They're typically pretty small, and but I made them a similar color as the background, so you can see it's the ones that didn't come up with a solution are highlighted in red. So most of them are generates a solution for. 92% of them we get an answer for directly that way using the elevation model itself. This is just repeating what was said, zooming in. I'm going to show you a few examples of this connections. Again, 2 flow lines coming together, and a fill and spill line going down to the next isolated flow line, and then from there down. Here's one, again, it's 2 flow lines coming together, and then fill and spill line following the elevation model down until it hits the other network. So we have this geometry being generated. You know, the editors may want to make it look cleaner, but at least we've got a basis to go by. Additionally, we can use the hydrodem. It's a hydrologically modified DEM, and run this, and the program actually runs through that as well automatically. And we find 12 of those missing ones we can get a solution for that we didn't get before, and that brings it up to 93% that we have answers for in terms of and the geometry to connect them up. This is an example of one that was connected up with the hydrodam. A number of these are where the NHD has the network ending in a pond, and sometimes it has trouble determining the fill and spill path. In that case, using the elevation, but the hydrodem works fine to find a connection. Another issue is that that a bunch of them, the ones that are not, we don't find solutions for, come really close, and for some reason the program doesn't work as in cases where it's often very close sometimes. But by simply, in terms of just knowing where they are and where they should connect, about 40 of these downstream end sinks are within 50 meters of a targeted flow line. And so using that tabularly, we can identify what the next flow line downstream is, really bringing the number of matches up to 97% in this particular HUC. And so I should point out that we have results, not only the physical line that's being created, but we're creating a table that gives the flow line ID of the downstream end of the isolated network, and also the ID of the flow line, the NHDPlus ID. I call it target ID here, of the receiving flow line. So this is another product that's being produced, and we're gearing up to do this nationally. These are, again, how many isolated networks we're working with per HUC. We're actually starting mainly because of the fact that Hydro Region 1 is the next one in the production process, but in terms of the NHD processing. So we're actually starting with the easiest one, which is probably a good thing. And the process is to create these. We run a pre-process procedure which helps to avoid certain errors, and then we run the fill and spill program, which is already programmed, and then we do a post-process to identify the target flow lines. And basically, we're gearing up to do this, starting with Hydro Region 1. And that's it for my slides.
Okay, Rich, could you back up a slide? Yeah, this one I wanted to mention on this, that fill area, fill volume, and time to fill, those fields are also computed as part of this process. So, the generally what you would see if, let's say that the end of the flow line, the sink, is in a depression, we wanted to compute to see, how much volume does that depression have, and that's the fill volume. And the fill area would be just the area of those cells that are covered in that depression when you fill it up and then make it and spill it over to where it connects up. And so we've got that information. We've also got the time to fill based off of the EROM mean annual flow. So I believe this is in days. I can't remember.
I think it's in days. Yeah.
Yeah. So we've got more information about these connections, and there's a lot of questions to still answer, things about, like, how do we decide which connections to make, which ones not to make. Then we can make these connections both in this tabular form, the way that is shown with the table. Let's see, I guess it was the previous slide or the next slide, I can't remember, the one that shows the table connections, Rich.
Well, this is the table connections.
Oh yeah. This is it. So so we can make these connections just in a tabular form, and we can do that sort of as an interim step. And later on, we can go in and add the actual connections themselves. A lot of questions to be answered about that, whether like what kind of feature we should make those connections. Do we use connector feature, or do we need a special type of feature code, an F code for this sort of connection? Bunch of questions that we still have to answer on this. But I wanted to show everybody this so that you kind of know what we're doing. You may see, if you're a steward, you may see some of these connections showing up in the markup. Some of the initial ones that are I mentioned earlier, the really large drainage areas that need to be connected up. Some of those have been showing up in markups, and some of the stewards on the call may have seen some of those. So again, this is all sort of evolving, but we're trying to develop ways to make this network much better connected so that it can be used for hydrologic modeling purposes, basically. We are a little bit over the end of the hour. I will stick around here for questions. I'm going to see if I can answer one question from Tara Mano about populous areas in Region 1. Yeah, I mean, we know that a lot of times in built-up areas, or where we lose streams, they end because they go into a built-up area and they couldn't see the channel anymore in the aerial photography. Maybe it goes underground or something. So those are all kind of questions that we're still trying to sort out. But this process hopefully will give us an idea of where those things ought to connect to, at least based off of the DEM. And we're still, there's a lot of questions to answer, I think, still. Yeah, I think that's probably, we're 5 minutes over, so we'll try to answer some of the questions, maybe separately, the ones that show up here in the chat. I want to thank Cindy and Rich for presenting, and hope that this has been informative for everybody. And we will see you all in a month. It'll be the fourth Tuesday of next month will be our next advisory call. So thanks for coming, and we'll see you next time.